So what I want to do now is look at a big example problem with some real world context, the type of problem that you might see on an AP exam. So for these normal calculations, we're going to follow a 3-step process. Step 1 is going to be to state the distribution. The way we're going to do that is to draw out the curve and label it. Then we're going to perform our calculations, and you have to show your work. Now, we're going to be doing this with a calculator, but you still must show your work. So I'll show you what that looks like in just a second. And lastly, we got to answer the question. So don't forget this part, it's important. We got to make sure we take whatever we found out and write it out in a sentence with some context. Okay, so the problem we're going to look at is a tennis problem. So we've got some data from the 2008 Wimbledon tournament where Rafa Nadal was serving an average of 115 miles per hour for his first serve with a standard deviation of 6 miles per hour. So we're going to assume that distribution is approximately normal to answer these questions. Cool, so we've got some data, it's approximately normal, we've got a mean of 115 and a standard deviation of 6 miles per hour. So let's take a look at how we would answer, oops, there's the answer. Let's take a look at how we would approach this problem. Okay, so we want to do our 3-step process. Step 1 is to draw the curve and label it. So we're going to sketch out a normal curve. Let's practice getting real good at this bell shape. You can see I'm not great, but that's okay, it's just a sketch. All right, so a really quick way to label your curve, and this is totally acceptable to do on the AP test, is with this notation right here. So N for normal, and then we list our mean and our standard deviation. So I pulled the mean from here, and the standard deviation was 6. Cool, so this little label right here that I made, that's enough to satisfy that requirement. You could also write a quick sentence that says, our data is approximately normal with a mean of this and a standard deviation of that, but this is faster. Cool, now that we have our curve drawn, not drawn super well, but sketched out here, we can go ahead and start labeling some things. So I know my mean is in the middle, since it's nice and symmetric. So it's 115. And then I have an idea about where a standard deviation falls on the normal curve, right at that inflection point. Again, it's just a sketch, so no need to be stupid precise here. All right, so if our standard deviation is at 6, each one of these little gaps represents 6 miles per hour. So this next point would be 109, 103, and so on. We can label the rest of these as we go. If this were the real AP test, I'd spend more time labeling some things. Okay, so our question is, what proportion of his first serves would you expect to be slower than 103 miles per hour? So let's find 103 on our chart, or on our density curve here. It's right there. We're looking for slower than 103 miles per hour. So everything to the left of 103. Cool, so we can see that this is a tiny sliver of our normal distribution, right? It's pretty far to the left. It's 2 full standard deviations below the mean. So we're wondering what is the proportion under the curve? What percent of the area is that little chunk? Okay, so we've got our curve drawn and it's labeled, and we visualized what we're looking for. Okay, so not only did we draw the curve, but we've got a little sketch of exactly what are we calculating. We're calculating this little area down here. So not only is this going to satisfy requirements of the AP test, but it's also going to give us a visual. If I get an answer that's like 30%, I know I did something wrong, because this should be a tiny number, right? We can see that's a very little chunk of our total area. Okay, next we gotta actually do our calculations, and we are gonna use the calculator here, but we're still gonna have to show some work. So what I'm gonna do is use Normalcdf in my calculator. So that's second distribution, Normalcdf. And then I'm gonna have to put in some information. So on my work here, what I'm gonna do is actually write it out. So this does count as showing your work. I'm showing them what I did in the calculator to get my answer. Okay, so I'm going to tell them what I put in the calculator, but I'm going to make sure to label what I inputted. And that's not exactly what I put in, but it'll work. I'm going to do this on another row here to save some room. So we can use the calculator instead of using sort of the old school method of looking up values on table A and things like that. So this is a totally acceptable method, but we do have to explain ourselves pretty well. I do want to show exactly what I put in the calculator and showing that I understand what's going on. My lower bound was a negative small number, my upper bound was 103, my mean, my standard deviation. Cool, let's throw that into the calculator. And we'll get 0.0228. Cool, so that proportion is about 2.3% of the total area. So that answer makes sense, I'm happy with that. Now we can do step 3, the important part here, answering the question. So what proportion of his first serves would be slower than 103 miles per hour? So we would expect .0228 of Nadal's serves to be less than 103 miles per hour. Cool. So we just took our answer, 0.0228, and threw it into a quick sentence with some context. First serves is what I should have said. That's okay. Cool. So that's our 3-step process. All right. So the next couple problems are really similar to the one we did on part A, with some slightly different numbers. So I've already worked through these, but I'll quickly go back and kind of walk through what I did. So part B says what proportion of his first serves would exceed 120 miles per hour. So again, sketched out the curve, kind of guesstimated where about 120 would be based on our mean and standard deviation. And again, this isn't a perfect sketch, just something to help me visualize what's going on. Threw it into my calculator, Normalcdf with a lower bound of 120, upper bound of a big number, big enough to make sure we capture all the data, and we get a proportion of 0.202. So about 20% of his first serves, 0.202 of his first serves will exceed 120 miles per hour. Cool, so we saw a sort of lower left tail problem, a right tail problem. Part C, we see an interval. So this one says what percent of Nadal's first serves are between 100 and 110 miles per hour. So again, we can sketch out what we're looking at and use Normalcdf to get this calculation. This time we do have a lower and upper bound that's defined, so from 100 to 110, and we get a proportion of 0.196. Notice on this one though, they asked for a percent. The other ones just asked for the proportion, so we just kept that number that we got. This one specifically asks for what percent, so I took that proportion, 0.196, and quickly turned it into a percentage, right? Just multiplied by 100 to answer the problem. All right, let's take a look at D and E, which are slightly different. Oh, there's some stuff down here, sorry. All right, on part D, it says the fastest 30% of Nadal's first serves go what speed? So this problem's a little bit different. We're still going to go ahead and sketch this out. So we draw our normal curve. We'll do a little bit better than that. We've got a mean at 115 and a standard deviation of 6. All right, this time they say the fastest 30% of Nadal's first serves go what speed? So this time we don't know what our observation is, but we do know the area. So this time we're working backwards. So I got to figure out where would I put the top 30%. So I think that's going to be right around here. Back up just a little bit. Right around here is where I'm thinking. Now, you might be wondering where I'm getting these estimates. How do I know where the top 30% of the area is? One thing we can do is think about our empirical rule a little bit. We know that about 68% of the data is within one standard deviation, and we can visualize where one standard deviation would be, right at that inflection point. So to get the top 30%, I need to back up some from that. So I'm thinking about maybe a half standard deviation away or so, maybe a little bit more. So again, this is just a sketch. It doesn't have to be perfect. So this time we're looking for what x value, what serve speed would give us an area of 0.3, 30%. Right, so we know this proportion is 0.3, and we want to kind of work backwards. So since we're working backwards, we're going to use a slightly different tool in our calculator. Instead of Normalcdf, we're going to use inverse norm. So inverse norm allows us to input an area and get out an observation. But you want to be really careful. On this version of the software, we only have one option for area, and it's always the area to the left of our observation. So even though the problem presents what's the fastest 30%, we want to find what x value would be at the 70th percentile. All right, so by default, inverse norm looks at the left tail area. Some newer versions of the TI software allow you to select left or right tail, but the default is left. All right, so below. So notice again, I put 0.7 for our area because that's 1 minus 0.3. All right, and then we put in our mean and standard deviation, and it should tell us what x value would give us, what x value would give us that top 30%. All right, so x was equal to inverse norm. Again, we want to show our work kind of the same way. We have an area of 0.7. We have a mean of 115 and a standard deviation of 6. So we get 118.15 miles per hour. Cool, and based on our little sketch here, that makes sense, right? It's about half a standard deviation away, all right? That looks pretty good. All right, and last but not least, we should always write a quick sentence. So this problem's gonna make us think a little bit harder. It says a different player has a standard deviation of 8 miles per hour, and 20% of his serves go less than 100 miles per hour. If the distribution of serves is approximately normal, what is the average? So this time we're not given the mean, so we've got to figure that out. So again, I'm going to kind of sketch this out just to help me think through the problem. We've got a normal distribution. We know the standard deviation, but we don't know the mean. So mean, I'm just going to say mu because I don't know what it is yet. Standard deviation is not 6, but 8 this time. Okay, so don't know our mean yet. We'll just call it mu for now. But we do know that the slowest 20% of the serves go less than 100 miles per hour. So again, we can kind of map out where would 20% be a little bit less than 1 standard deviation below, because by our empirical rule, 1 standard deviation below leaves about 13 or 14% of our data. So 20% is a little bit more than that. All right, so this is 100. That's the x value that cuts off an area of 20% or 0.2. Okay, so how do we take this information and work backwards to figure out our mean? We can't use inverse norm this time, even though we have the area. Inverse norm requires us to know the mean. We know the standard deviation, but not the mean. But what we can do here is we can standardize our data. So this can be really good practice to do on all of these types of problems, but the calculator makes it so that we don't always have to standardize. If you were using table A, you would do this for pretty much every problem, but we only have to do it for something like this. So the standard normal distribution means we take every single observation and turn it into a z-score. So the result of that is that our mean becomes 0, and each standard deviation becomes a standard deviation becomes 1. Right? Our z-scores describe how many standard deviations away a value is. So when we standardize our data, we get this same distribution every single time. Now what's really nice about that is I can take the same bit of information, area is 0.2, and I can calculate the z-score that would give us a proportion or an area of 0.2. All right, so we are going to use inverse norm. An area of 0.2, and then we have a mean of 0 and a standard deviation of 1 since we're using the standard normal curve. And I get a z-score negative 0.842. Cool. So by standardizing this and finding this value on the standard normal curve, essentially what we've done is we found the z-score for 100. right, 100 miles per hour, has a z-score in this distribution of negative 0.842. Now, if we know our z-score formula, then we should be able to figure out the mean. So as a reminder, a z-score is where we figure out how many standard deviations an observation is away from the mean. So we take our observation, we subtract the mean, and we divide by standard deviation. So our observation is 100 miles an hour. We don't know the mean, but we know the standard deviation is 8. And we know that 100 has a z-score of negative 0.842. So we should be able to get to the mean now with just a little bit of algebra. So I'm going to multiply both sides by 8. Can subtract 100 from that. Oops. 100 from that. Negative 106.733 equals negative mu. So mu is 106.733 miles per hour. I'm going to cut off some of those digits. Just add our units. All right, so we found our mean, 106.7 miles per hour. As always, we want to throw this into a quick sentence to finish this off. So this player had an average serve speed of 106.7 miles per hour. Cool. So using our calculator, we can find the area under the curve for a given interval, whether that's the left tail, the right tail, or some interval in between. We can use inverse norm. If we already know an area or proportion or percentile, we can find an observation value from that using inverse norm. And if we have some missing information, we don't know the mean, or maybe we don't know the standard deviation, but we know the data is normal, we can use the standard normal curve to find a z-score, and then using our z-score formula can figure out that missing information.